So in this video, we will see about approximation algorithms. So approximation algorithms are kind of algorithms that are used to solve the NP-hard problems. So NP-hard problems are the problems for which we don't have any polynomial time solutions. So these problems, already existing algorithms takes exponential time to solve these problems. So by using these approximation algorithms, so we can develop approximation algorithms for the same NP-hard problems with polynomial time complexity, but the main difference is these approximation algorithms cannot able to deliver the exact solution. They can able to give a near optimal or closer output, closer to the actual output. So, for example, we can take a traveling salesperson problem, TSP problem. So this is DSP problem is to find a minimum cost path to cover all the cities. For example, if the given input, the minimum cost is 200. So if you solve this TSP problem with actual existing algorithm, that is branch and bound algorithm, it will gives it takes 2 power n time to solve it, but it actually always give the exact solution 200. But for the same TSP algorithm, we can develop approximation algorithms. But the approximation algorithms don't always gives the correct output 200. So sometimes it gives 250, or sometimes it gives 300. So which are near optimal or closer to the correct output. So this is actually the approximation algorithm. So the approximation algorithms have some approximation rate. So approximation rate means the actual difference between the actual output. In this case, this is 200, and the derived or delivered output. So in this case 200. So each approximation algorithms contains such kind of approximation rate that is called R. So example for this approximation algorithm is Vertex cover. So we already know Vertex cover is a NP-hard problem, so which cannot be solved using polynomial time. The actual algorithms takes exponential time 2 power n. So actual problem statement is this is a graph problem. So we will given a graph, and from that graph we need to find a minimum number of vertices or a subset of minimum subset of vertex which covers all the edges in the graph. So in the real-time application, suppose for example, if you are working as a network engineer for a company, and your company have billions of servers installed all over the globe. So you need to install some security mechanisms like intrusion detection systems or firewall software in to protect your entire network. So we need to find a minimum number of servers. So from that millions of servers, we need to find a minimum number of servers. If that protection software, firewall or intrusion detection system is installed in that servers, then it covers all the systems, entire network. So this is the Vertex cover problem. Just we need to find a minimum number of vertices in the graph which covers all the edges. So this is the given input. That input contains 7 vertices and 7 edges. So we need to find a minimum number of vertices which covers all the edges. So in actual approach, how this can be solved means so we need to find all the possible permutations of all the possible combinations of the subsets. So since for example if your graph contains only 3 vertices, so all the possible combination of the vertices is 0 0 0 0 0 1 then 1 0 0 1 1 0 1 1 1 0 1 1 1, so and so on. So that means 2 power 3. There are 2 power 3. That means 8 such combinations are there, and we need to check for each combination whether it covers all the edges. And from all the combinations which covers all the edges, we need to select which combination contains minimum number of vertices. So this is the actual solution for this vertex cover problem. So if the number of vertices in that graph is n means, so there are 2 power n combinations are there, and for each combinations we need to check whether it select all the edges or not. So in total it takes O of 2 power n time complexity. So for the same vertex cover algorithm, vertex cover problem, we can develop a approximation algorithm. So this approximation algorithms follows the greedy approach. So initially, that result set C, vertex cover set C is initialized as a empty set, and E dash is contains, that means we copied all the edges in the graph to E dash, and while E dash is not empty. So until the E dash becomes empty, we need to do this process. At each iteration, we need to select one arbitrary edge. So in any edge from that graph G, arbitrary edge U comma V from that edge set E dash, and these vertices U and V. So if we select one edge means in each graph the edge always contains 2 vertices, 2 n vertices. So these 2 vertices U and V are added into the result set C. Once that vertices U and V are added to the result set C, then the edge, actual selected edge U comma V, as well as all the edges which are connected by the vertex U and V. So all the edges to which the vertices U and V are connected, that edges also should be removed. So this process should be repeated until the set E dash becomes empty. Then finally the set C contains all the vertices which cover all the edges in the graph. So set C contains vertices which cover all the edges in the graph. Suppose for this graph, initially you select the edge 1 to 2. So then we add 1 comma 2 to that set C. So and all the edges which are connected by 1 and 2. So this edge is connected by 1, and this edge is connected by 2, and this edge is connected by 2. So we need to remove these edges, and we need to select some other edge from this graph. So the remaining edges are edge from 3 to 7, edge from 4 to 5, and edge from 3 to 5. Suppose if you select the edge from 3 to 5, so you select 3 and 5, you add these 2 vertices into the result set C. Then we remove this edge, and this edge should be removed, and this edge should be removed. So now all the edges, we cover all the edges with these 4 vertices. So now we can able to find a set of vertices which covers all the edges in the graph. And the approximation rate R for this approximation algorithm is 2. So that means if the actual minimum vertex cover size is n for the given input means so it can able to find a minimum vertex cover from the size from n to 2n. So and then the time complexity of this approach is O of V into E. So V is the number of vertices and E is the number of edges. So it is a polynomial time algorithm. Thank you.